Hello and welcome back to this second lesson in our course on the planets of the solar system. In our previous lesson, we explored how the planets are organized within the solar system, delving into the division between the inner and outer regions. This distinction not only reveals the incredible diversity of our planetary family, but also tells a story of stark contrasts. In the inner solar system, we find the small, rocky terrestrial planets, dense and rich in metals. As we move outward, we encounter the massive gas giants composed primarily of hydrogen and helium, and finally, the icy outer worlds, where frozen elements dominate. Each planet's unique composition and characteristics reflect its own remarkable journey of formation and evolution, adding to the rich tapestry of our solar system. In this lesson, we'll turn our focus to one of the most essential and fascinating elements in the universe: water. This seemingly simple molecule made up of just two hydrogen atoms and one oxygen atom holds extraordinary power. It shapes the surfaces of worlds, drives planetary processes, and perhaps most importantly, offers us the key to understanding the origins of life itself. So join me as we uncover the profound role water plays, not only on Earth but across the solar system, and explore how it has influenced the planet's stories and their potential for hosting life. But why is water so pivotal? What makes it a cornerstone in our quest to understand the solar system and ultimately the universe? For one, liquid water is widely considered essential for life as we know it. Here on Earth, it serves as the solvent of life's chemistry, providing the medium for biological reactions and enabling the complex systems that sustain organisms. It stands to reason, then, that the search for water elsewhere in the solar system is not just about cataloging planetary compositions, it is about exploring the very possibility of life beyond our own world. Yet water is much more than a potential harbinger of life. Across the solar system, we find water in its many forms: liquid, ice, and vapor, playing critical roles in the evolution and dynamics of celestial bodies. It carves landscapes, fuels volcanic activity, and forms ice caps and ocean worlds. From the subsurface oceans of Europa and Enceladus to the ancient riverbeds of Mars, the presence of water speaks to the past, present, and future of planetary environments. As we delve deeper into this lecture, we will explore the prevalence and significance of water across the solar system. What does its distribution tell us about planetary formation and history? How does it shape the potential habitability of distant moons and planets? And most tantalizing of all, could it harbor signs of life? On Earth, water manifests in an extraordinary array of forms, from the delicate condensation of misty fogs to the immense power of torrential rain, from the delicate crystals of snow to the relentless flow of mighty rivers. These forms are interconnected through the planet's dynamic water cycle, a system that continuously recycles water across its various states. This cycle not only sustains Earth's ecosystems, but also underpins the planet's ability to support life, making it a vital component of Earth's habitability. What truly sets Earth apart in the solar system, however, is the presence of standing liquid water on its surface. Oceans, lakes, and rivers define the planet's landscape, influencing its climate, geography, and biodiversity. Liquid water is foundational to life as we understand it, and Earth remains the only known celestial body where this vital substance exists in such abundance and accessibility. But what about elsewhere in the solar system? Does water exist beyond Earth, and if so, in what forms? While Earth's surface water is unparalleled, frozen water ice is far more widespread across the solar system. In the colder outer regions, many celestial bodies are enveloped in thick layers of ice, hinting at the universality of water beyond our planet. The moons of the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, are particularly notable. Almost all of these moons are sheathed in icy crusts, which serve as frozen barriers to what might lie beneath. Europa, one of Jupiter's Galilean moons, is a standout example. Its surface is a frozen expanse of water ice, yet beneath this icy shell, evidence suggests the existence of a vast subsurface ocean. This ocean is kept in a liquid state by tidal heating, a phenomenon generated by the gravitational interactions between Europa and Jupiter. Such findings elevate Europa as a prime candidate in the search for extraterrestrial life, as its subsurface ocean may harbor the conditions necessary for biological activity. Closer to home, Mars offers another fascinating case study in the search for water. Although liquid water no longer flows across its surface, the red planet harbors significant quantities of frozen water locked in its polar ice caps. The northern polar cap, an expansive deposit of frozen water spanning roughly 1,000 kilometers across, contains a volume of ice equivalent to about half of Earth's Greenland ice sheet. These polar ice caps are not merely frozen relics. They serve as archives of Mars's climatic history. Geological evidence, ancient riverbeds, deltas, and lake beds, points to a time when liquid water likely flowed on the Martian surface. This raises tantalizing questions. Was Mars once a more hospitable environment? Could microbial life have existed in these watery past landscapes? The widespread presence of water in its various forms challenges us to think beyond Earth-centric notions of habitability. From the suspected subsurface oceans of icy moons like Europa and Enceladus to the frozen reservoirs on Mars, water's versatility raises profound questions. Could these environments support microbial life, even in extreme conditions? How did water come to be so widespread across the solar system, and why is it concentrated in particular regions? Such questions drive contemporary planetary exploration. Missions like the Europa Clipper aim to investigate the Moon's ice-covered ocean, while rovers like Perseverance on Mars search for signs of ancient water and the possible biosignatures it might have preserved. Water, in both its frozen and liquid states, is far more prevalent in the solar system than once imagined, appearing in environments that defy initial expectations. Its presence in such extreme and diverse locations challenges traditional assumptions about where water can exist, offering profound insights into planetary science and raising tantalizing possibilities about the habitability of distant worlds. From the parched, sun-baked surface of Mercury to the frigid depths of icy moons, water emerges as a unifying, mysterious element central to our understanding of the solar system. Mercury, the closest planet to the Sun, is a world of extremes. By day, its surface temperatures soar to a scorching 800 degrees Fahrenheit or 427 degrees Celsius, hot enough to melt lead. At first glance, this seems like the least likely place in the solar system to find frozen water. Yet paradoxically, Mercury harbors water ice within its permanently shadowed craters near the poles, regions shielded from sunlight and nestled in perpetual darkness. How can ice persist in such an environment? The answer lies in Mercury's lack of an atmosphere. Without an atmosphere to distribute heat, the sun's intense energy only affects regions exposed directly to sunlight. The craters at Mercury's poles, shrouded in shadow, remain untouched by solar radiation. These cold traps create conditions where temperatures plunge to hundreds of degrees below freezing, allowing ice to endure for potentially billions of years. Moreover, Mercury's tenuous atmosphere means there is little pressure to cause the ice to sublimate or transition directly into vapor. This preservation mechanism allows scientists to study ice that may date back to the earliest days of the solar system. Could these ancient reservoirs hold clues about the origins of water in the inner solar system? Mercury's icy paradox opens a window into the complex interplay between heat, cold, and water in unexpected environments. While Mercury demonstrates the surprising persistence of frozen water near the Sun, the outer solar system reveals another marvel: vast subsurface oceans of liquid water concealed beneath icy crusts. These hidden oceans exist in some of the most intriguing celestial bodies in the solar system, including Jupiter's moons, Europa, Ganymede, and Callisto, and Saturn's moons, Enceladus and Titan. Take Europa, for example. Beneath its bright, cracked ice surface lies a global ocean of liquid water, kept from freezing by tidal heating, a process in which gravitational interactions with Jupiter generate internal heat. The resulting energy is enough to maintain an ocean beneath an ice shell that could be several kilometers thick. Europa's dynamic surface, marked by ridges and fractures, provides visual evidence of these tidal forces at work, hinting at the movement of water beneath. Ganymede, the largest moon in the solar system, is another fascinating case. Its subsurface ocean, likely layered between icy shells, further highlights the diversity of these hidden water reservoirs. Enceladus, however, offers the most direct evidence of subsurface water. Geysers of water vapor erupt from cracks in its icy crust, spewing materials into space and revealing the interaction between its subsurface ocean and the Moon's surface. These plumes even contain organic molecules, raising compelling questions about the Moon's potential for life. These subsurface oceans are astonishing not only for their existence but also for their scale. In fact, the total volume of liquid water hidden beneath the surfaces of these icy moons is believed to far exceed all the water on Earth. Enclosed beneath layers of ice, these oceans are insulated from the harsh temperatures and radiation of space, creating relatively stable environments. Could they host life? The presence of liquid water, combined with the detection of organic molecules on moons like Enceladus, has propelled these worlds to the forefront of astrobiological research. What makes these environments even more intriguing is the potential for chemical activity. The interaction between liquid water and rocky cores, as might occur on Europa or Enceladus, could provide the energy sources necessary to sustain microbial life. Similar processes occur in Earth's deep-sea hydrothermal vents, where life thrives in complete darkness, fueled by chemical energy rather than sunlight. Could such conditions exist elsewhere in the solar system, deep beneath the icy shells of these moons? The solar system continually challenges our conventional understanding of water by revealing phases and states that are entirely foreign to terrestrial experience. While on Earth water exists in its familiar solid, ice, liquid, and gaseous states, certain environments in the outer solar system, particularly within the ice giants Uranus and Neptune, introduce us to exotic forms of this essential molecule. These distant worlds reveal the extraordinary ways water can manifest under extreme pressures and temperatures, offering insights into physical processes that extend far beyond Earth's boundaries. Among the planets of the solar system, Uranus and Neptune, often referred to as ice giants, are remarkable for their water-rich compositions. Unlike their more massive counterparts, Jupiter and Saturn, which are dominated by hydrogen and helium, Uranus and Neptune are primarily composed of water, along with significant quantities of volatile compounds such as ammonia and methane. At first glance, their outer atmospheres might seem misleading, with their vibrant blue and blue-green hues attributed to the presence of methane gas. However, beneath these visible layers lies an extraordinary narrative of water undergoing transformations unlike anything found on Earth. The term ice giants belies the complexity of their interiors, which are not dominated by frozen water as we know it, but by water subjected to unimaginable pressures and temperatures, leading to entirely unfamiliar phases. Deep within the interiors of Uranus and Neptune, water undergoes remarkable phase transitions that challenge traditional concepts of matter. As pressures climb to hundreds of thousands of bars and temperatures soar into thousands of degrees, water transitions first into what is known as the ionic phase. In this phase, the extreme conditions disrupt the structure of water molecules, or H2O. The intense pressure causes the hydrogen atoms to dissociate, while the oxygen atoms form ionic bonds, creating an entirely new material that behaves differently from liquid or solid water on Earth. Even more extraordinary is the existence of superionic water in the deepest layers of these planets. Under pressures exceeding 1 million bars, over 1 million times the atmospheric pressure at Earth's surface, and extreme temperatures, water takes on a superionic state, an exotic phase where the material behaves as both a solid and a liquid simultaneously. In this phase, oxygen atoms form a rigid, cage-like lattice structure akin to a solid framework. Meanwhile, the hydrogen atoms, now ionized, move freely through this lattice as a fluid-like flow of positively charged ions. This unique combination of rigidity and fluidity allows superionic water to possess properties that defy classification within traditional states of matter. In our next lesson, we will delve into two crucial phenomena that help us better understand the dynamics of our solar system. One of these phenomena is cooling. All planetary bodies, from the smallest asteroids to the largest gas giants, are constantly cooling by radiating heat into outer space. This cooling process is driven by the fact that the interiors of these objects are incredibly hot. But here's the fascinating part. cooling doesn't always look the way you might expect. There are various ways this process unfolds, some of which may surprise you. For example, the cooling of planets can influence their geological activity, atmospheric conditions, and even the potential for habitability. Remember to subscribe to this channel to stay updated on the planets in the solar system. Thank you for now. See you next time.